Okay, so let's start. So today I plan to go over the different concepts that you have been learning and studying, and then after we will likely have enough time. I can talk a little bit about the current like Lab 3A, and maybe spend a little bit of time on the last task that seems to be difficult. So yeah, what have you been doing? So I'll go from the start, and just in this one slideshow you effectively see what you have been doing. So first of all, we were talking about how to code up which pins are going to be output or input, and we have the DDR register for that to set that for you, and then the port and the pin registers allow you to either read, actually write or read. So now this you have been using a lot, that was also one of the first lectures that we talked when we talked about registers in general. So debouncing of signals, so we're interested in a button push, a switch, and the idea is that you actually see this kind of behavior, and if you are going to poll the switch on whether it is going from low to high, well, in this very short time interval you see a whole bunch of rising edges. One, here another one, two, and here another one. But it's pretty clear that it takes a little bit of time for that switch to settle in this particular picture. So what you want to do is you want to implement debouncing, and what we did was, well, you can do things in hardware. You can do it as well in software, and effectively what you do is you sort of do a read and then wait and verify methodology. So you see a rising edge. Okay, great. Let me wait for a little bit and check somewhere over here again whether it's truly high, and then I have a confirmation. So it's really about reading. You get either through a polling mechanism you see a rising edge, or through an external interrupt that gives you, for which you have set up an interrupt service routine, and that routine catches that you see a rising edge. Well, then you want to wait a little bit, and then you want to confirm your measurement, whether you truly saw change towards high, and that is what you can do in software. As I said, in two different ways. One is through detecting the rising edge through polling, and then you simply wait, or through an interrupt service routine, for example an external interrupt, and again you wait, and then you will figure out whether it was really true that you saw a button push. So here's a four-state debound state machine that you actually have been working with a three-state state machines, but why not have a quick look at what a four-state machine could look like, just to reiterate this type of concept. So a finite state machine represents different states, a no push in this particular case, and then I have two maybe states that in what you have been studying so far has been merged into one central maybe state, and then out of the maybe push state I may go to pushed, and out of the maybe not pushed state I go to no push. Now in this particular diagram we effectively will always remain in no pushed if I do not see a button push, but if I do see a button push, for example here, then I go to the maybe push state, and I will confirm later on, say 30 milliseconds later, whether that is really true, and if it's really true I go to the push state. And when I still am, if I still press the button, I'm still pushed, I'll stay in this state, but at some point I may release the switch and I'll go through the maybe not push state, and I'll check, say 30 milliseconds later, that it's truly indeed the case. Then I go to the no push state. Now in this particular in this particular finite state machine, you can also clearly see where you could add more things along the edges. For example, if I see here an arrow from maybe pushed to pushed, then I know for sure I transitioned from no push to maybe push to pushed. And then I can add something over here, like an event. For example, I thought over here that I'm going to that the button is pushed, and I may record a time, and 30 milliseconds later I confirm that, and I may say the event that I've measured over here is indeed correct. It turns out that that was the moment that a button was pushed, and I sort of validate that event by adding it to my list of events or some computations that I'm doing currently, like in a stopwatch. And similarly, if I have a no push, well, that may also mean something in some kind of interface that you would like to build, and you can register the no push event over here, and then when it is truly confirmed in this transition, I can do some computation with it if I want to. Now, different solutions are where the two maybe states are glued together, and you sort of build in a little bit of memory, another variable that remembers for you where you come from. So if I come over this edge, I will sort of say my last state equals no push, so that when I'm in the maybe state, I know that the last state was from no push. So if these two are merged into one single state, then I will update my last state over here to no push, while I update my last state over here to pushed. So in the maybe state, I always then know, because I have added a global variable that remembers for me where I come from, where I'm actually coming from, and through that mechanism I can then also implement accordingly when a certain event was recorded according to a button push, and then 30 milliseconds later confirmed, and I can do some computations. So this is yet another solution for making that happen. Okay. So we talked about the LCD data write and also command write, of course, but here we only have this particular example. And in the library, you will see that for an LCD data write, you see 4 pieces of code. Here they are, separated by 1 millisecond to make sure that the final state machine in your LCD screen is actually settling. Now, these are very long waiting times. We've exaggerated a little bit over here. According to the data sheet, as you may have seen, you can get away with, I think, 40 microseconds over here, and so on. But my point is that you want to make sure that everything is reliable, and for your interface, like for a human, it really doesn't matter if you wait a little bit longer. Problem, however, is that if you wait a little bit longer, it may not matter for the human, but it does matter for resource sharing on your MCU. So if you simply wait, then you essentially block all the computation for whatever else you're doing. So you like to make sure you share resources, and you want to make sure to make that non-blocking, meaning that these delay functionalities are avoided, and that you can still do some other functionality. And the way we were doing this is to use a timer that can, through its hardware interrupt, can indicate when a millisecond actually has passed. And if that's the case, I can then forward a piece of code to the next stage. And actually this becomes then a finite state machine, right? Where I start over here, and if there's indeed something to write, I will execute this code. Then I need to wait for the interrupt service routine for the timer to make sure that 1 millisecond has passed, and I'll execute the next code. I update the state again to start from here next time the interrupt service routine triggers, and then I execute this and then that. Now, we saw, by the way, that in the LCD screen assignments, you sometimes would like to introduce also a command write. So not just a data write, you want to have a command write, like clearing a whole line. Now, if that happens, well, you again use the same methodology, but then the command write is immediately followed by your data write, and all of a sudden things may start to become desynchronous. It's like you have 2 separate threads that you would like to execute, but effectively you need, in this particular case, the command sequence to finish before the write sequence for data can start. So that you need to remember somehow. You can do it in different ways, like a busy signal or whatever it is. and then or a larger finite state machine, which is the final solution that we talked about in the last assignment. Now, here's a picture for what happens, right? If you have blocking writes, then the main program will work. You have an LCD write, then you have to wait for a millisecond. It's wasted cycles. You do the next piece of code, you wait again, next piece of code, wait again, and finally you get out and you have, in a sense, waited for 4 milliseconds. So if you have this non-blocking writes, you effectively execute a piece of code, but then you get out of this LCD write functionality, and you have time to do all kinds of other executions in main by calling other procedures, other functions. So that's how you then save the cycles. All right. Now we talked about interrupt service routines. Actually, after that, well, not actually, sort of at the same time, and I think I've asked these questions in your problem set. So anyone who likes to answer these questions? So it's very important that these types of answers really are sort of fixed within inside you, because the ISR is the fundamental core, if you will, for MCU programming. So you need to understand how an interrupt service routine really works. So what's going on with that thing? So who calls the interrupt service routine actually? Is it the main program that does this? Or anything else? Any thoughts? Is the instruction that is calling the interrupt service routine? No, right? You know? All right. So it's. Sorry.
It's not like it's like you don't really like. It's not like calling it in the traditional sense, but it's just basically waiting for a change, whether that's like a flag variable or something else. Like you don't, you're not calling it like our ISR parentheses.
Yeah, you don't call it in the software itself, but it is being called automatically when a flag is set for the interrupt service routine. So actually the hardware is calling that interrupt controller. Now, can you pass a variable to an ISR? No, right? We cannot do that. But what's important to realize, though, is that you can still manipulate variables in your ISR. If you treat them as global variables, then they will be visible outside your ISR. So that's the way around it, right? So it's not that you pass a variable, but you can still manipulate variables, like global variables. And so what's the return value of an ISR? Does it have any return value? No, it has no one, right? Nothing. So, and then how does the actual hardware know where to find the code for the corresponding ISR? Well, that comes from the table, right? So from that interrupt vector table. So if you're looking at that interrupt vector table, which is also good to remember, you see all the possible interrupts that you can find. They're all here. They're all ordered also according to priority. Because what this interrupt controller is doing, it's going around in a round robin fashion, but whenever an interrupt service routine finishes, it starts from the top. So it will first handle the interrupts, an interrupt that relates to a reset, and next to an external interrupt, then to pin interrupts, then to a watchdog, then to the timers, and a lot of stuff around timer interrupts, all the way down to here. Then we have some communication, which is all this stuff, and finally it's about the analog to digital conversion. So what happens is that right at the start of the program memory, you have these addresses loaded in these positions. At address 0, you see some kind of address. At position 2, you see another address. It's a address that contains, as you can see, 1, 2, 3, 4 hexadecimal symbols, so it's 16 bits, it's 2 bytes, and that's why you need jumps of 2 to 4 to 6 and so on, because you need 2 bytes of memory to code this address up. So what happens, you have in the main memory, the main code is, for example, located over here, and you start executing, and you get to that instruction, but after that instruction say, there is some external interrupt happening, int0. That flag corresponding to the interrupt is set, the hardware is catching it, the interrupt controller is catching it, and it looks in that table and notices, I need to jump to this address. So there it goes to this address, and now it is doing all this stuff that I talked to you about, like saving all the register state, the program counter, like where was I before the actual interrupt happened. I stored it on a stack, meaning just a set of addresses stacked on top of one another, and then I'm going to execute this. Now at the very end I'm going to restore all the register state, and I'm going to pop off the stack that particular address where I should go back to, which is right there. And that's what's happening. And now I can continue my other instructions in the main program. So this is how this execution of an ISR works. Now then we talked about timers. So timers is a great machinery. They have added quite a lot of machinery around it. So for example, we have these comparators. You can clock them off according to, a scaled internal clock. You can compare to a register that can indicate how you are going to show data over or values, high or lows over a channel called channel A. In this particular case, channel B for a second comparator. And then you can also create, of course, by programming it properly, you can enable interrupt service routines, interrupts, and on a trigger where this is equal, you can then do several things. For example, you can clear this register over here, which is the essential counter that counts up all the time, or when this happens, go to the interrupt service routine that you wrote for it. So there's different modes of operation. Here we just stress, say, two modes. Say the normal mode, the timer counts up from 0, and at some point it overflows, say at 255 in this particular case, because the timer 0 has 8 bits, right? And then an interrupt can be generated upon an overflow. You could do that. The CTC mode is a different mode. Here the OCR0A is loaded with some value between 0 to 255, and the timer counts up from 0, and then on a compare match with that register OCR0A, which is when that occurs over here, then an interrupt can be generated upon the compare match, and then also the counter can be reset and cleared to its initial value of 0. So here we see in this table, so definitely look at the data sheet. You see in the tables you see the normal mode, here you see the CTC mode, and you see that you can indicate what you want by programming these 3 positions in the various control registers. Here we see control register 0A, TCCR0A, and here TCCR0B. And here we see the 3 positions, W, G, and of waveform, right? Wave generator mode 00, 01, and 02. And I simply have to code this up to 1 if I want to be in a CTC mode, meaning that I'm looking at TCCR0B, TCCR0A, and I set this position to 1, which I can then do by ORing a left shift of 1 over WGM01 positions, which would make a 1 move 1 position in this direction, exactly over here, and OR that with the actual default value of the register that you see here. So this will become a 1, and then you will have programmed the waveform, the wave generation mode. Now, you also would like to enable several interrupt service routines that you want to program. So one is the overflow interrupt. So let's have a look what that mean? So we started, so when it comes back to 0 and it goes to 1, to 255, overflow occurs, then it calls, because you have enabled it, the hardware calls this ISR. You have some code that you can then execute, so that's one option. Now you can also work with the compare match A interrupt, and here we again have the same thing. When equality, when the comparison happens, then you will execute this particular ISR. The hardware again gets triggered to do so. The main program gets interrupted, really, right? No, just the final instruction is finished, and then it goes into this interrupt service routine. So, what was this? Oh, right. Now timer 1 is a tiny bit different from timer 0 and timer 2. First, it has 16 bits, so that's why we have FFFF, right? The timer overflows at 65,535. And in addition, we have that, well, we'll come to that in a moment, but that you can also capture interrupt. So here we have the tables, a different chapter, 15 as you can see here. So now we have 1, 2, 3, 4 positions in order to indicate the different modes. And you have a bunch more other possibilities to play with, but for now we've only focused on normal and CTC mode. And here are the 4 positions that define in these 2 registers, the TCR1B and TCR1A, with which you can define the mode of operation that you would like to use. Now the big difference, another big difference, besides having 16 bits in your counter, meaning that you have a high and a low 8-bit value in your counter, you can also do a capturing of this counter. And that can be steered in 2 different ways. First of all, you need to do a write enable, and it can be triggered on, for example, a rising edge over here or a falling edge. I will indicate it in this position in the corresponding register. I have a noise canceller here. Okay, you can indicate whether you do 1 sample or 2 samples. If you do 2 samples, you're able to be more sure about whether the value that you see is indeed the correct value, a high or a low. So that cancels some noise. But important is this particular multiplexer, this position in the corresponding register, the ACSR over here, indicates whether I like to feed this signal, this edge detector, from this source or from this source. Now this source is simply a pin, a PB0 in this particular case, over which I can just generate some kind of rising, falling edges that are then being detected by the edge detector. Now I can also, and that's what we did, create an analog comparator. An analog comparator can then compare, for example, these 2 pins. We only used 1 pin and compared it to a bandwidth gap that is using an internal piece of circuitry. But that essentially will generate then your highs and your lows, or your rising and your falling edges that are being detected over here. So the hardware performs now this particular instruction. So the ICR1, when this is indeed being triggered, this particular value, ICR1, gets the current value of TCNT1 immediately. And clearly, when this enabling signal is given, you can also immediately, if you have enabled the corresponding ISR, you can then if it's enabled, it will then execute the timer capture factor interrupt, and you can write some code over here. So for example, in the current lab that you're going to work on now is again a stopwatch methodology, which you should reuse your old code. And the only difference that you would like to make now is to, rather than just directly reading TCNT1, you would like to implement this particular interrupt service routine. So you can think about how you're going to use this particular methodology over here. You can you can think about it yourself, and you clock that off, and at some point you actually want to trigger this, and then you capture the actual counter. So if I have a stopwatch, I usually click and so forth, and if I click again and on that particular button push, would be nice if it's connected somehow, that I can then trigger immediately this capture interrupt service routine. That would be nice. And then I can have some code that can then register that event by just reading ICR1, right? So some variable becomes that ICR1, I will transform it into actual time, like milliseconds or whatever it is. So that's how you can think about this. Now, we also talked about external interrupts. So we have the external interrupts INT0, INT1, and they are a little bit more advanced than the pin change interrupts. Now, there are 3 pin change interrupts corresponding to 3 sets of pins, 0 to 7, 8 to 14, and 16 to 23. And here are the pin interrupts, right? And here are the external interrupts. And what you can do is you can configure the corresponding control registers to indicate for external interrupts whether you want to trigger on a falling or a rising edge. Over here you can enable some pins, only those pins that you're interested in, to trigger, say, the PC10 or PCI 0, and then of course you can enable this, and this will then call an interrupt service routine if you have enabled it on a pin toggle. So regardless of the falling or rising edge, when it toggles, either it falls or it rises, you will then call the interrupt service routine. Now, we talked about how you could implement some atomic code with that. That would be really cool if you really want to keep that uninterrupted, so you can do that. We talked about how you could effectively simulate the falling or rising edge interrupt by using this interrupt, by simply figuring out, by measuring whether the current pin has a high or a low, whether the toggling came from a falling or from a rising edge, and that will then allow you to do the right whatever thing you want to do. So here we have these control registers, and we can talk here about the ISC11 and 10, and here it's talking about a falling edge and a rising edge. That's the ones that we are using all the time. And if I want to enable the interrupt service routine for this particular external interrupt, I have to set this bit to 1. And for the pin interrupts, we see the same. We have, I can, for example, enable the PCI 0, and then I also indicate. Wait a minute. So where is that? Oh yeah, and then I indicate which of those pins I would like to program to trigger this particular interrupt. So I have pins 0 to 7 in this particular case. Happens to be the same numbers of this, but there's no relationship. So here we have that these 3 pins, if we set those 3 to 1, that those pins, if they toggle, they will then call that will lead to a call to the interrupt service routine for PCI 0. Yeah, so we have a similar mask for register 1 and for register 2. If we would have enabled those and those, we would also set some of those pins. Oh, that's it. Okay, any questions about this part? So this is pretty much like an overview of the different kinds of mechanisms that you have been working with. I've not talked about task-based programming in here, which is the underlying way you guys are moving forward with all your assignments, and effectively the machinery, or how do you steer peripherals, how do you work with interrupt service routines and so on. That's what I've been talking about in this review session. So if there are any questions, do ask me, and if not, then we'll continue with what you guys have been doing in Lab 3A, and then maybe we can talk a little bit about the third task as well. All right, so let's do that. So